So the Thevenin'S theorem is saying that if you have a circuit of this sort, and then most of the times, let's say you're looking at it from this direction. Let's see, somewhere, let's say here, not necessarily looking through there, but like you're constructing it from these points here, right? So here, say there's some terminal of the whole circuit here, but you're looking from this side here, right? So we basically want to see what's happening there, right? Like through these terminals. What it says is that you can simplify this whole circuit and in the end you get something like this, right? But then because we are looking through this terminal here, you are looking through this C and D, we bring back this R3 which is here, we bring it this R3, bring it back here, the same R3 is here, right? But it makes it easier to find whatever which is here, which is the current passing through this R3 here, right? But everything here, which is the voltage sources, have been simplified to 1. The resistance have been simplified to 1. So that's all what the Thevenin's theorem is about. It basically helps you to simplify the circuit, right? Looking at the whole circuit from a particular terminal, right? Looking at it from a particular direction. So this is what we're going to do. What we've done so far is that you've seen that in applied electricity, the basic equation so far, if you remember this concept, I think most of the times you'll be fine. The basic thing so far is that in applied electricity, what we do is we use this equation. This V is equal to I. We've said it, but I'm saying it again, right? So if you are following the Thevenin's theorem, one way to do is that, meaning that we are trying to simplify the circuit, right? And what do we see? We say that we change all this to 1, this 2 change to 1. But the only thing that has not changed is what we are looking at it from. So basically, we are looking at it from this direction, right? So from this terminal C and D, the ones in green, right? So meaning that this doesn't change, which means that somehow, it's not always though, but our aim is to find the current flowing through this resistance here or through this terminal here, right? This CD here, which is the I in green that we are trying to find, right? So what we do is that then again, our main equation that we are considering is V is equal to IR, right? And by doing so, that's what we do, right? Minute. So we know that equation, there's a name for it. I forgot. It has escaped me at the moment. So we know that somehow our aim is to find the I, right? So we'll need, if our aim is to find this I here, right? So then that means we'll need the V and R, right? We'll need the V and then the R. And then when it comes to Thevenin's theorem, the simplest of these two, the V and R, is the R. The R is the simplest to find. So this is how we go about it. So basically, what the whole Thevenin's theorem is saying is that if you have a circuit of that sort, this is what we do in a minute. Okay. So as we were saying, I'm going to do a diagram. We've said it, but I'm going to use a diagram to demonstrate what the theorem says. Okay. That way, aside what we've said, it becomes clearer what we are doing. Okay. All right. Okay. So the first step to do any of this Thevenin's theorem is that we clear these out, right, and then we open circuit this side, right? So it becomes just a terminal, right? So a terminal, right? It's open circuited, right? This is the first thing. And then we said the whole equation that we are using is V is equal to IR, right? And then our aim is to find what? This I here, right? So then to find the I, the ones that we need will be V and then R. And then among these two, we said R is the easiest to find. So if R is easiest to find, then we've simplified the circuit. Let me a minute. Let me do this. When we open circuit like this, we introduce this voltage here, right? But at the moment we don't want to put it there, but let me just put it there. I'm not closing the circuit, but I'm just introducing it so that we know what we do with it. Okay. So then V and R, which one is easier to find? We said it's R, right? So before you find R, this is how we do it. Meaning that we are trying to find the effective resistance within the circuit. That's, you are looking at it from this direction. That's why we have this terminal C and D, right? So what we do here is that let me just draw a free diagram. Okay. So what we do here is that the same circuit, right? But we remove everything aside the, what do you call it, the resistances, right? Everything aside the resistances. So we have this, right? And then this is still open circuited. and then let's use the symbols just there so that we know what we are looking from. Basically, we said we are looking from the terminal C and D, right? So this is what we do. And now that we have these resistances, our aim is to find the effective resistance, right? We know here is 2, 3. Then we've discussed this already. Clearly, if you understood that discussion, you could clearly see that these two here are in parallel, right? So if they are in parallel, this is what we do. Minutes. If they are in parallel, that's where we have the product over something, right? Whether 2 or 3 or whatever the number of resistances, is all the same because they are in parallel. That's the way we find them. Okay. If it's for 2, that's why we have product over sum. But if it's for 3, there's a formula for it. Okay. But because there are 2 here, we go straight for it. Alright. So product over sum. So the effective resistance here, which we basically call the internal resistance because we are looking at it from here. So anything else within this side, right, is what we will consider internal resistance, which is a small r, right? So that's why we have product over sum. Product, which is a 2 here, times a 3 all over the sum of these, right? So let's see. 2 times 3. Then again, this formula only works for 2 resistances, right? Because it is the bigger formula that I'm simplified to this one. Product over. Oh, this is sum. Okay. Product over sum. Okay. Then again, it works for only 2 resistors, right? Or 2 loads. Yeah, because we are finding effective resistance here in parallel 2. Right, so basically, the internal resistance here, small r, is 1.2 ohms, right? Okay. So now we found what we said our aim is to deal with because our aim is our original aim is to find the I, right? We will need what? V and then R, and then the 2, which one is easier to find? R, right? So now our aim is to find V, right? When it comes to Thevenin, finding the V in this case, we usually still go by the V is equal to IR, right? Because now we have the V, we can find the R inside this part. We are able to find V now, right? So we found the R, right? Then we can easily find the I first before we can find the V, right? So this is what we do. So what we do is that we still consider this circuit here, this one right here, right? For us to be able to find what's the name? To find our I, right? Which will help us to find our I, right? Which will help us to find our V. So this is what we do. So now we could see that whenever there's an open circuit, current cannot flow through that side because now we are trying to find V, but we need I, right? Current cannot flow through that side. So we know that I itself is equal to what? V on R, right? Okay. So then we have R, what we need is what? V. But then looking at this one again, let me circle this, right? The only place that current could flow, because now we are finding current, is this side, right? Current cannot flow here because here is open circuit. That will be a very difficult part to take. It will not use that side, right? So this will happen. The V, we can see clearly that this V here goes in this direction, right? Because this is the positive, right? This is also the positive, right? So then, if you remember, what was the name? Oh, there's a name for that. Something current law. Yeah, Thevenin's current law, right? Or Thevenin's law. There's a name for it that escaped me, but yeah, if a current so we know here is positive, right? So basically this one will move in this direction, the current from this voltage source, the one from this source will move in this direction, right? So for the current law, there's a name for that, but what we know is that the algebraic sum of the voltages in the circuit is equal to the sum of the loads in the circuit. So basically what it goes the same with the V is equal to IR, right? But you put all the V's here, right, and you put all, which is the voltage sources, and these are, so we know clearly that this one is the positive, this one is the positive, so this one voltage moves here, this one voltage moves here. So as we were saying, we're basically doing the sum of the voltage sources, right, and then the sum of the loads, right? But then we still consider direction. So looking at this one very well, but our aim here is to find V, what? I, right? So this I will be, the voltage sources we know is 6, and then and 4. But then this is what we are looking at. Let's go over this again. That's why we introduced this v here initially, and as we said, we're going to talk about it. What's happening here is that we are trying to look for this v here is trying to represent every voltage inside here. So if everything here is moving in this direction, a minute, everything we are looking for everything from here, but here this one moves here. So this v here, you are trying to find the equivalent voltage within the internal, or what do you call it, inside of the circuit, right? So that's what we are doing here. So what we do is that I is equal to sum of the v, which because, so let's try and determine the directions, right? So we can see clearly that this one moves here, right? This v is going in this direction, so the direction that we will use during our calculation should be in this way, right? Because we are looking for what equivalent. So the direction that we'll be using our calculation is this. This will be a positive in the calculation we are doing right now, because this v introduced here is this way, pointing this way. So right, so if they get here, they should be equal at this point, right? So they cancel out each other. So the direction that we are using during our calculation is this. Okay, so get to calculation. So the v here, which one is having this direction? This 6. So that one is positive, right? Positive, right? The other v, then again, you are considering this loop within the circuit. The other direction, the other voltage source is this v, but this one goes in this direction, which is opposite to this one, so negative, right? So minus 4. Now we look at the resistance. Clearly we can see that if we are considering this loop, right, if we are considering this loop, so we are just seeing it as if nothing else is here, right? So what happens is that we see these ones to be in series, right? So that's what we do, is just 2 plus 3, right? Yeah, so then again we are still looking at this one, right? So we are considering just this loop, but then these elements are here. So from what we've done so far, you get from the introduction, you get to know that because these elements are here, we can move across them without passing through any other element. Then they are in series, so 2 plus 3. So that will give us our current that we are looking for to find the voltage finally. So this will be 6 minus 4, and then we have 2 plus 3, and that gives us 0.4, right? 0.4 amperes. So this finally gives us 0.4 amperes, right? So we started with saying that we're actually trying to find this I, right, which is v is equal to IR, but we need this what we're trying to find, but we need R and then V. We were able to find the R easily, right? The V we can't find directly, so we use again under v is equal to IR. We found the R, and then sorry, we are using v is equal to IR, but then to find this V here, right? But then we needed the I, so we found the I using this V on R, right? And now that we know the I, we can find the V. So now we have this V here, which is this one that we introduced here, right? We have that V. So basically we can simplify the circuit. So this is what we do when we are trying to simplify the circuit. So we look at the original thing. So let's see. Okay, so the internal resistance has already been simplified, right? Which is, we had to be the small r, right? So we basically can represent that with just 1. So let's see, we end up getting, let's take this out. If it's, since it's just, a minute, internal resistance first, right? So meaning this one goes off, right? And now we have just this, and we said that internal resistance, the small r, is what, 1.2 ohms, right? 1.2 ohms, right? Okay, and now we simplify the V as well. Where is that? Oh, we have this I now. Let's see, where do we put a V? Okay, we have this I now. So now we've not found this V yet, right? So the next thing will be to find the V. So let's take this down. Let's take this somewhere. Okay, so now we have the I that we need. Now the next thing will be to find this V here, this one right here, right? So this is how we go about it, meaning that we'll be looking at just that circuit, right? So let's see, that will be, and what happens here is that we will be considering this loop. Let me clean this and make it clear. Let's clean this up. Then again, we use loops when we are doing circuit analysis, right? That makes whatever it is that we are doing easier. Right. So now that we found this I here, right, the next thing we do is that we'll be able to find this V here easily. But then we'll be using a different loop. Remember we use this loop, right? So now we're using another loop to help us find the V that we're looking for. Right. A minute. Okay. Oh. Okay. So now this is what we do. Then again, what are we doing? We're considering this loop here. So this is what we do. You know that in order to find this V, this is what we do, right? We put this V here, right? So let's just do what's the name? Current on one, what do you call it? Voltage sources on one side, and then the loads on the other side. So if this is V here, meaning this direction, right? You clearly see that this direction, right? So if we are doing so, then again we are considering just this loop. This 6 here, right? Meaning that everything here is not being considered because we are using what? Just this loop, right? Just this loop. In fact, at times we even label the loops to make it easier. We use something like, let's see, A, B, C, D, E, F. So let me just use that. Okay, let me just use that. So now we are considering a loop. Let's see. A, C, F, D. This is D, right? Okay. So loop A, C, F, D, right? So this is what we do. So doing that, we can write the voltages, right? So this one is going in this direction. We are choosing our conversion to be this way. Depends on you. So we are going this way, right? If we are going this way, the next voltage source that will meet is this one, but this one is this positive terminal, so it's going this way. So to be in opposite direction, which is gives it what? -6. Now we use the loads, right? When we are considering the loads, this is what happens. If we are still moving the direction that we started with, right? So you choose a direction and you stay consistent with it. Okay, so we are choosing this direction. We are here, right? So if we are moving this way, the next current that we encounter will actually be this one, right? Which we found to be this I here, right? So this I basically moves this way. So since is a, what do you call it, a current, and it moves into opposite direction, we just do a minus 0.4, and then because here is low, we need the R. What's the R for that one? We actually said this. Where is it? 2, right? So 2 here. So this right here will help us get our V here. So let's see. Okay, so we have X. Well, that's what we're trying to find. Right. Well, let me put everything exactly. X, right, -6. Right, and then we have bracket minus 0.4, and we have 2. And we are trying to find X, right? So let's see. So that gives us what? V to be 5.2 volts, right? So that's our V. So meaning that, you see, we found the resistance. This is the circuit I drew initially. We found the internal resistance and we simplified everything, right? Simplified everything, and so we can clear all these, right? And then we have just this, representing the internal resistance. We found that, right? So now our next will be to put in the voltage source, because we have two, this and then this, but we want something, just one, to represent everything, right? And which we found now to be the 5.2. So we can clear all this, right? All this cone, right? And this becomes the 5.2 that we just found. This V here, let's just make it V. This V becomes for 5.2 what? Volts, right? So that's it. So that's it. The initial circuit, that bigger one that we had. So let's bring it. Let me also. This is the original thing. The original. Let's just add this. Okay. So this is the original circuit, right? That we've simplified all these voltage sources, this and this, into just this, right? and then you simplify this and then this to just this, right? But then because we are looking at through this terminal as we said, we maintain this R3 here, which is still 10, right? But then what we're seeing, aside being able to simplify the circuit, we are able to find the current passing through this terminal here. So with that we can find it easily now that we have this circuit. So let's clean this up and see how we'll be able to do that. When you simplify it this way, it makes it easier. That's why we see circuit analysis, right? So now that we have all these components, we will be able to find the I that we circled, the I that was here, with an I here, right? Which is the current passing through this R3 here, right? So that's what we are trying to find. So this one, looking at it, very easy, right? So if you are finding I, then again our basic equation V is equal to IR, right? But we need what? I. So I will be what? V on R, right? Looking at this very clearly, the resistances are what are in series, so we can add them up, right? And then the voltage is what we see here. We can put it just there. It's just one, so that's 5. Right, as well. So we have here 5.2, which is in voltage, and then R, because they are in series, we've discussed this over and over. That gives us 1.2 plus 10, right? And that'll give us our I, which is the current passing through the R3. So let's see. That's a 5.2 all on 1.2 plus 10, right? And that gives us a current of 0.4. Let's do 4 dB, 4643 amperes, right? Alright, so that's it. Thevenin's theorem, circuit analysis.